This video is about IGBT. IGBT means Insulated Gate Bipolar Transistor. IGBT is also a power electronic device designed to handle the power levels in the electrical systems. Look at the rightmost figure showing the symbol of IGBT. You can observe IGBT is the integration of MOSFET at the input side and BJT at the output side. So IGBT is a three-terminal device with the terminals gate, emitter and collector. And because the input side of the IGBT is a MOSFET, IGBT is a voltage controlled device. The advantage of being a voltage controlled device is that continuous current is not required at the input side to control the conduction. So BJT is not used at the input side because the output current in BJT is controlled by the input current, and this needs continuous current at the input side, whereas in MOSFET the input current is zero because of the insulating layer. The advantage of MOSFET of having higher input impedance because of the insulating layer at the gate is utilized in the construction of IGBT. And IGBT is a power electronic device, right? So the conduction losses that we expect should be very less. We know that compared to MOSFETs, BJTs provides minimal conduction loss because of the bipolar nature and the low saturation voltage. When VCE is low, then the power loss will be low. So this advantage of BJT is utilized in the construction of IGBT. So IGBT is a combination of MOSFET at the input side and BJT at the output side. Now look at the construction of IGBT. IGBT is constructed with four alternating layers of P-type and N-type semiconductors. The layers are N plus emitter region, P-type body region, N minus drift region, and the P plus injection layer. The emitter electrode is connected to the N plus region, and the gate terminal is insulated with a silicon dioxide layer, and the collector electrode is connected to the P plus injection layer. The P-type body region is the body of IGBT. Now let us understand how the IGBT works. When we apply a positive voltage between the gate and the emitter terminals, an inversion layer is formed under the dielectric layer. Because a positive voltage at the gate pulls the electrons from the p-type body region and thereby forms an inversion layer. With the inversion layer, a low resistance path is created for both holes and electrons to flow between the emitter and the collector terminals. Because of this inversion layer, the electrons from the N plus emitter moves into the p-type body region. So whenever electrons moves from N plus emitter into the p-type body region, the current starts flowing. Till now, the operation is similar to a MOSFET. Now, the operation of BJT comes into picture. Here, the construction is like a PNP transistor, which is p-type body region, N minus drift region, and the P plus injection layer. So whenever the current starts flowing at the p-type body region, the electrons from the N plus emitter which reached the p-type body region enters into the N minus drift region. And observe that N minus drift region is a lightly doped N region. It is lightly doped because when the device is off, it should block any high voltages at the emitter. We know that the width of the depletion region is inversely proportional to the square root of the doping concentration. Light doping means width of the depletion region is higher, right? Then the electric field spreads over a larger area because of the wider depletion region. So a higher voltages can be blocked without reaching the breakdown. Whereas in heavy doping case, the width of the depletion region becomes smaller and the electric field is less, so the breakdown occurs at the lower voltages itself, which is not desirable. So remember, to act as an off switch, it should prevent the current from flowing even if high voltages are applied. Now everything appears good, but there is a trade-off here. A lightly doped region provides the advantage of blocking the high voltages in the off state, but during the on state, it provides high resistance, because of which the power loss can be high. So, here the concept of conductivity modulation needs to be implemented. Conductivity modulation means increasing the effective conductivity of the lightly doped semiconductor region by decreasing its resistance. This is possible by injecting the minority charge carriers into the drift region. So here the P plus injection layer injects the holes into the drift region, thereby decreasing the resistance of the drift region. And this minimizes the power losses, and we can deal with the trade-off that I have explained before. So finally the electrons move from n plus region into p-type body region and into the n minus drift region, and holes move from p plus injection layer into the n minus drift region, enhancing the current flow from the collector to emitter. This figure is the equivalent circuit of IGBT. Go through the circuit diagram to understand the direction of currents and the polarities of voltages. The figure shows the output characteristics and transfer characteristics of IGBT. The output characteristics are mentioned in the right side and transfer characteristics are mentioned in the left side. The transfer characteristics are between IC and VGE. So when VGE is less than the threshold VGE, the device remains in the off state. When the VGE crosses the threshold voltage, the device enters into conduction as shown in the transfer characteristics. And note that the forward output characteristics of IGBT is similar to that of BJT. This concludes the topic of IGBT. If you like the video, please like, share and subscribe to my channel. Kindly help me to help you.